Hello everyone, my name is Mike and I'm sharing 10 techniques that I have for improving your group delay measurements on frequency converting devices that have embedded local oscillators. For example, I'm talking about devices like this MyTech satellite block down converter, which takes a 20 gigahertz signal in and down converts it to about a 1 gigahertz signal out using an embedded local oscillator operating at 18.75 gigahertz. So I want to measure the group delay on a device like this, and I have 10 techniques that we can use to improve our measurement accuracy. Now, of course, I'm going to use the Rohde Schwarz ZNA vector network analyzer to make these measurements. This is an instrument that we introduced to the market about 1 year ago, and it's been optimized for making measurements on frequency converting devices like that MyTech satellite block down converter. Now, in particular, I'm going to use an option called K9, which is our two-tone group delay technique for measuring frequency converters like this. And for more information on this option, you can refer to application note 1EZ81, which goes in detail about how this group delay measurement works. But what we're doing in this series of videos is we're looking at different parameters that we can optimize on the network analyzer to make our measurement as accurate as possible. And we're seeing in real time what happens as we change these different parameters. Now, we're looking at the effects on the measurement that we're making directly on the instrument. So I have 10 different techniques for improving the measurement. Each technique has its own video. And in this video, I'm going through idea number 9. So I've already covered 8 ideas for improving the measurement. We've gotten the trace noise really good. And here is idea number 9 for making the measurement as accurate as possible. Now, this idea is to use attenuators at the ends of the cables to reduce mismatch, the impact of mismatch or reflections between the device under test and the network analyzer. So now this is not a new idea at all. Using attenuators to settle down mismatch is commonly done during measurements with test equipment. It's even done in the design of RF equipment. So I'm sure if we take this MyTech satellite block down converter apart, we will find attenuators installed between different stages to settle down the reflections inside the device under test. So using these attenuators is a fairly common thing. There's nothing wrong with it. If you think, oh, it's cheating in some way, that is not the case. We are trying to settle down reflections so that we can make our measurements as accurately as possible. Now, what I want to show you is the impact of using the attenuator during the measurement. So we're going to use the scripts that I've created up to now to set up the instrument in the optimal way, using everything we've learned so far, and then we're going to see the impact if I use an attenuator and don't use an attenuator. Now, before I do that, I want to kind of explain that these attenuators are not necessarily trying to improve the return loss everywhere to be the best possible. That is one goal that we want, but it's not the only thing. What we're also trying to do is minimize the impact of changing the mismatch from when we calibrate the device, when we calibrate the channel, to when we connect the device under test. So for example, I have a good return loss on my calibration mixer. So when I connect the mixer and I calibrate, what I'm really doing is normalizing my group delay measurement with that mixer connected. And by normalizing, that means I'm building a term into my normalization table that takes into account the mismatch or the return loss that I see looking into the output port of the calibration mixer. So whatever that mismatch is, it becomes part of my normalization table. And then when I disconnect the calibration mixer and I connect the device under test, I see a different mismatch, and it's that different mismatch that causes a problem. Even if the different mismatch is a good return loss and my calibration mixer has a good return loss, the fact that the return loss changes at all, even from one good state to another good state, it may have simply rotated to the other side of the Smith chart, that change is enough to cause me problems if I'm not using attenuators. And if I do use attenuators at the ends of my cables, I can minimize the effect of the changing mismatch. So let's see what that really looks like. I think it'll make more sense once we see it on the screen. So I'm going to start by connecting my calibration mixer with no attenuator on the output port. So I'm focused on the output port for these measurements, which is the low frequency port. In fact, it's at about 1 gigahertz. And I'm going to set up the channel and calibrate the channel with no attenuator on the output port of the calibration mixer. So let's do that using this GPIB Explorer tool. And let's select Open Script File number 9, which is Explore Attenuators to reduce mismatch. This says connect the mixer please, so that we can do a calibration run, and we do a calibration run, and then we say okay, and now I've got a calibrated trace, which is actually quite low now. We're down to 38 picoseconds. We're taking advantage of everything we learned in the first 8 videos to get this trace to be as clean as possible. It's got 38 picoseconds of peak to peak variation. This is getting to be a very small number, but I've calibrated with a calibration mixer attached, and my calibration, which is really a normalization for this group delay measurement, it has built into it the mismatch between the mixer's output and my VNA's input port at the calibration plane. That means if I change the mismatch, I'm going to see a change in this trace peak-to-peak noise. And I plan to do exactly that. I'm going to change the mismatch between the output of my calibration mixer and my network analyzer. I'm going to do it by adding this small piece of transmission line, which is laid out on a piece of FR4 printed circuit board. So all it's going to do is change the mismatch a small amount. It's not going to take the mismatch and make it much worse. I can tell you right now, the output return loss of the calibration mixer is on the order of 12 dB. And after I add this transmission line, it will still be on the order of 12 dB, but it's going to be rotating around on the Smith chart. So it's going to have different phase angles than what's expected. And that is what's going to cause the problem. So I'm not destroying the output match of the calibration mixer. I'm simply moving it around on the Smith chart to another region where it's still good. All right, so now I connect this mismatch, and what we see, and I'm going to zoom in a little bit on this. What we see then is new peak-to-peak variation that goes up as high as about 650 to 700 picoseconds. So suddenly I have a lot of variation on my measurement, even though I just calibrated with this mixer, and all I did was change from one good return loss on the output port of the mixer to another good return loss. So I'm just rotating around on the Smith chart, but it causes a lot of variation in my trace, and that's what I'm not happy about. Let's save that to memory so I can recall it later if I need to. And now what I want to do is repeat this exact same experiment, but this time I'm going to put a 6 dB attenuator on the cable, on the output cable that's going to connect to the calibration mixer, and I'm going to calibrate with the attenuator in place, and then I will change the mismatch again to see what the effect is. Basically, what I'm hoping for is that the attenuator will help to settle down this mismatch variation, and I will get a better result afterwards. So I'm connecting the attenuator to the cable, and now I'm connecting to the calibration mixer. And the result that I see on the screen, that's not relevant right now because it's not really calibrated for this particular setup. So don't worry about that. What I'm going to do is hide this memory trace temporarily. So I don't want to show it. And I'm going to go to my trace here, and I'm going to recalibrate now that I have an attenuator installed. So after calibration, I'm seeing again a similar peak-to-peak variation, but of course it is a little bit worse. If you remember, we had a peak-to-peak variation that was about 40 to 50 picoseconds. Now we're up closer to 100. Why would that be? Well, one reason is because I added this attenuator, I'm now getting 6 dB lower power to my receiver on the network analyzer. And when I have a trace that's this low in noise, this sensitive to variation, a 6 dB difference makes a big difference. So we can compensate that by just turning the power up 6 dB. And I want to do this because I want to keep it apples to apples with this attenuator test. So let's turn our power from minus 10 dBm up to minus 4 dBm, and let's calibrate this trace one more time. Okay, now I have a peak-to-peak variation that's in this 40 to 50 picosecond area. So I'm equivalent to what I was before. I've added the attenuator, but everything after calibration is the same in both cases, with the attenuator and without the attenuator. Now let's see what the effects are of adding a little bit of mismatch to the output of the device in the test, just to retune the reflection angle. Where I know before it caused me to have peak-to-peak variation that was on the order of 700 picoseconds, I want to see if that variation is lower now that I have a small 6 dB attenuator on the ends of my cables. Okay, take a look at that. Let's get this tightened up a little bit. But now that I've changed the mismatch, my peak-to-peak variation is on the order of 180 picoseconds. That is significantly lower than when I did not have the attenuator in place. So just as a reminder, let's go back to the memory trace. When the attenuator was not in place, we had this blue trace with about 700 picoseconds of peak-to-peak variation. With the attenuator in place, repeating the exact same experiment, our peak-to-peak variation is down to 180 picoseconds. So the lesson here is that these attenuators at the ends of our cables can help settle down mismatch. They make us more immune to the changes in the reflections that occur, even when we have a good return loss during calibration and a good return loss during our measurement. The fact that the return loss phase angle can rotate all the way around the Smith chart on us and still be a good return loss, that's a problem that our normalization technique is susceptible to. These attenuators will help with that technique. So now, that's idea number 9 on my top 10 list of things we can do to improve our group delay measurements, and it's an idea I definitely take advantage of as often as I can, but I have one more idea left, and this one is the best of all. This one coming up in video number 10. This is an idea that I've been waiting for a long time, and now we have it in the Rohde Schwarz ZNA Vector Network Analyzer. I cannot wait to show it to you, so please tune in to video number 10.